Yeah, this talk is about the age and chemical characteristics of the 3 billion years old lunar meteorites, basaltic meteorites. And for the next 12 minutes, I will try to show you how peculiar they are. So let's start with a quick overview of the lunar basaltic volcanism in terms of volcanic activity. We know it spanned between 4.4 and 1 billion years, distributed in two phases, with the younger one between 3.4 and 3.1 billion years. And the topic of this talk is what happens at the end of this phase. In terms of chemistry, we can distinguish three groups. The first one, the crypt basalts, they are enriched in potassium, rare earths, elements, and phosphorus compared to the other lunar basalts. And we believe they are derived from an enriched source. We have the group of high titanium basalts. And finally, we have the dominant group of low titanium basalts. This group can be subdivided into several subgroups. And for the purpose of this talk, I will just mention the low mu basalts because they have a low uranium-238 to 4 lead ratio. These basalts are derived from a source with a low mu ratio, a depleted mantle source. And finally, we have the 3 billion years old basaltic meteorites. In terms of mantle sources, we believe that these basalts were derived from sources created by the crystallization of the lunar magma ocean, or LMO. And this crystallization process terminated at 4.4 billion years. In terms of sampling, most of the basalts we have are originated from this area, the Procellarum crypt terrain. That's where we have recovered the crypt basalts, but most of the basalts we have from this area tend to show a crypt component in their mantle sources. So let's have a closer look at the 3 billion years old basaltic meteorites. We don't have much data, in fact. If we look at the age, we have few samples with a robust age at 3 billion years, like there's 3 samples collected from Northwest Africa. But that's not the case for all the samples. And for some samples, we have no agreement about the age. There's 2 samples collected from the La Paz ice field. And this could be related to analytical or methodological issues like terrestrial contamination. So we don't have a well-constrained time frame for this volcanic event. And in addition, we have an age overlap with another meteorite, Northeast Africa 003, which was dated at 3.1 billion years. But this date is not really precise. In terms of chemistry, if we start with the rare earth elements pattern, we have some similarities between some samples. In terms of radiogenic isotope ratios, we have few data. Some samples have been investigated for strontium and neodymium isotopes. And we have just only one sample with robust lead isotopic ratios. So altogether, we don't really know if we have a single volcanic event at 3 billion years. That means we cannot really interpret the chemical data. That means we don't really know if what is the origin of this volcanism. So to tackle this issue, we targeted these 2 samples collected from the La Paz ice field. We also investigated Northeast Africa 003, And we analyzed this meteorite found in 2020, which happened to belong to this group. In terms of analytical technique, we applied the in situ lead-lead dating technique by secondary ion mass spectrometry. Just a quick word about this approach. Basically, we construct a 7646 lead isochrone with in situ analysis of minerals containing lead. Typically, we target minerals containing initial lead and or radiogenic lead. That means phosphates, potassium feldspars, sulfides, and bedelites. This figure here is an isochrone. You have the 4:6 ratio here on the x-axis, the 7:6 ratio on the y-axis. And here you have all the minerals analyzed in a given sample forming a regression, the isochrone. The intersect of the isochrone with the y-axis gives us the composition of radiogenic lead. And with this formula, we can calculate an age. At the upper extremity of the isochrone here, we have the composition of initial lead. So let's have a look at the results. That's the isochrones for the 4 investigated samples. And what you can see is that the ages of the samples are similar, and this age is also similar to the robust data we already have. In terms of initial lead isotopic composition, the 4 investigated samples show the same isotopic ratios, and those ratios are also similar with the robust data we already have. So with this information, we can define clearly a volcanic event and a chemical group at 3 billion years. So we can have a look at the chemical characteristics of these lunar meteorites. And starting with the rare earth elements, here you have the patterns of the 3 billion years old meteorites. What you can see, they are all similar, excepting probably Northeast Africa. But what you can see in this image, the texture of this sample is very coarse. It's probably accumulate when you compare with the more fine-grained texture of the other samples. If we compare with the patterns of the other low titanium basalts, the 3 billion years old meteorites have enriched rare earth elements patterns. So we can suspect an enriched source. So we can have a look at the strontium, neodymium, and isotope ratios, and we can start with lead. Here in this diagram, you have the 4:6 versus 7:6 lead isotope ratios. And here you have the composition of all the lunar basalts investigated so far. What you can see in this plot is that we can explain the isotopic composition of the lunar basalts by a mixing between a low mu source, a depleted source, and a creep-like source. That is true for lead, but it works also for strontium neodymium. However, the 3 billion years old meteorites do not fit this model. So that means that there is no creep component involved in the source of these basalts. And because the other lunar basalts with creep component in their mantle sources are originated from PKT, that means the 3 billion years old meteorites are probably not originated from PKT. So how can we decipher the mantle sources of the 3 billion years old meteorites? Well, we can construct theoretical curves showing the evolution of the isotopic composition through time. So this is what you see in this figure. You have these curves that are that describe the chemical evolution of the basaltic sources. And these curves are governed by this kind of equation. So here you have the 6-4 ratio, but you have the same type of equation for the 7-6, for the 7-4, I'm sorry. So basically how it works, the composition of the source at a given time is a function of the composition of the source when it's formed. It's function of the mu ratio of the source and the time since the formation of this source. The problem, we don't know these parameters. We cannot solve this equation unless we make assumptions. In fact, we have to make a lot of assumptions, and that weakens this type of model. So we decided to go for another approach, which is Monte Carlo simulations. Basically, how it works, we make vary these unknowns parameters, and we check the calculation if they reach a convergence. So we tried that with a basaltic source derived from the LMO, and that didn't work. So we tried it with a depleted mantle, and then we got some results. And this is what you see, this green curve describing a theoretical source for the 3 billion years old meteorites. We calculated also an age for the formation of this source, 4.1 billion years. That means after the solidification of the LMO. We calculated also a mu value for this source, 1200, which is what we would expect for an enriched source. In summary, in terms of chronology, we have one volcanic event clearly defined at 3 billion years. In terms of chemistry, the 3 billion years old basaltic meteorites require an enriched source, but no creep component involved in this source. That means that these meteorites are probably not originated from PKT. The source form probably at 4.1 billion years. That means after the solidification of the LMO. That means that the source of these meteorites is probably not directly derived from the LMO crystallization. Thank you.
Thank you very much. We've got time for 1 or 2 questions. I'll start with one. Is there data that supports the fact that these samples are all launched together, or would there be more different launch events?
I have no idea, actually. Some stones are paired, and they were probably ejected from the moon at the same time, but we probably need to investigate that. But honestly, I don't know.
Okay, thank you. There is a question at the back. If we can have a microphone at the back.
Hi, Renaud. Here is Anna Czernok, University of Trieste. Are we sure that this has to be a volcanic activity, or the source of basalt can be a different kind of melting? Can they be impact melt crystallized basalts?
They look like basalts. As you can see, it creates somehow a problem to have the source formed after the crystallization of the LMO. That's if the model is true, of course. If they are products of an impact, we should have other evidences. But
okay, great. Thank
I
you
will
very
not commit
much,
myself.
Renaud. So we will move to the second talk of the session.